Alright, we are live. I'm going to be going live just a little bit early today, every time, because I've noticed that it takes it a minute for people to like cycle through and get in. Uh, that being said, I'm going to go to the Blended Learning website. I'm going to give it a minute for people to log in and get access to the class. Because most people don't start trying till 8:45, and it might take a minute or two. Oh, let me open up one more thing. So today we will be in Transformers. All the way down at the bottom. And magnetism and electromagnetism is the lesson we're going to be on. Everything will be in chapter 1 of your textbook. We do have a few media clips for you to watch if you want to. Alright, let's get started. I'm going to be putting up a thing every time we get in that just, I'm going to leave it up for a few seconds. So if people are watching later, they can have a screen that will pop up as they're scrolling through and be like, oh, well, here's the beginning. Nah, try not to put the actual lesson questions up until after we've started. Alright. Blank is a force that acts at a distance. That's magnetism. It's a lesson about magnetism. Magnetism is caused by a magnetic field. That's pretty on the nose for it. A ferromagnetic material is easily magnetized. Examples of a ferromagnetic material is iron, nickel, cobalt. Let's see, iron, nickel, cobalt, neodymium, like the small magnets, the small really strong magnets, rare earth magnets. Those are all ferromagnetic materials. A permanent magnet holds its magnetism for a long period of time. Permanent magnets don't just refer to things that are naturally magnetic. If you magnetize your screwdriver, that would be a permanent magnet. So things that aren't permanent magnets are things like electromagnets. Whenever you power it up, it becomes a magnet. And then if you take the power off of it, it's no longer magnetic. There's no residual magnetism. It's just immediately, it has a force acting upon it that is making it magnetic. And then as soon as that force is gone, it's not magnetic. A material is magnetic if it has organized molecular magnets so that the individual fields add together. Yeah, so inside of a piece of material, the atoms or the molecules of that material they have poles. They have a north and a south. And what magnetizing something does is it straightens all of those out to be pointing the same direction. And their magnetic fields will add together at that point. Before, they're facing all sorts of different directions and canceling each other out. And the more of the molecular magnets you straighten out and get pointed in the same direction, the stronger the magnet. Electromagnetism, kind of talked about that earlier. If you wrap a wire into a coil and put a charge on it, it will have a magnetic, or if you put a charge on a wire, it will have a magnetic field. If you wrap it into a coil, that multiplies its magnetic field and lets it build up really good. No, I just said that. Alright, which of the following magnetic qualities is analogous to the electrical equivalent of voltage? This word means the same as, or equivalent to. And that is magnetomotive force. If you go to page, and I have a cheat sheet, page 6 in your textbook, the transformers, hold this in a way that doesn't have a glare. Maybe. Yeah, the Transformers textbook. You can look all these up. Everything will be in that book all day. Have your blended learning website open, and you can see what chapter we're going to be in for each of these. And that's super useful. Blank is the opposition to magnetic flux in a magnetic circuit in a given column of space or material. That is reluctance. Reluctance is the opposition to magnetic flux. So reluctance is analogous to resistance. If you look at the chart on page 6, it gives you all of the measurements that have to do with magnetism and what they are equivalent to in electrical theory. Yeah, reluctance is how much a material opposes magnetic flux. An example, in I think it's permeability. Reluctance is like if you had a magnet and you could see the magnetic fields. If you moved something with a lot of reluctance into that magnetic field, you would see it distort the magnetic field, and like the magnetic field wouldn't go through that material. That's if you could see the magnetic field, you would be able to see the strength of those flux lines around the magnet. There is a experiment where they take iron filings and they put a magnet and then underneath like a clear sheet of plastic, and they sprinkle those iron filings on the plastic, and the filings will like gather in the flux lines. It's actually pretty neat. The strength of the electromagnetic field and the current are directly related. Yes. So if you are powering an electromagnet up, the more current you put to it until you hit saturation, the more current you put to it, the more powerful of a magnet it will be. But depending on the material and the makeup of that coil, will determine how strong it can possibly get. Permeability is how accepting something is of a magnetic field. It will be the higher the permeability, I believe the better it makes for an electromagnetic core. So I kind of explained saturation. The the whenever you hit a or put a circuit at saturation, you can go higher with your current, but it's not going to give you anything in the flux density category. It's not going to make the magnetic field stronger. Okay, we already answered that one. If transformers are operated at the point of saturation, waveform distortion can occur. So you're supposed to have a nice clean sine wave whenever you are operating a transformer. But the closer you get to saturation, the more that nice sine wave is messed up. Let me see if I can find. Yeah, this is a pretty decent picture of it. I mean, all of these are not bad pictures of it, but you can see your correct sine wave is here, and there's all sorts of different disturbed waveforms. Hysteresis. Hysteresis is if you've ever like changed, like messed with something and the like turned a knob and it didn't directly control something, like you would turn something up and then later the other thing would move. That's hysteresis. There's where it's like it just kind of lags behind a little bit. A good way to see that is in your house if you have a AC unit kick on and your lights dim just for an instant. That's because your transformer is taking a second to catch up with the new load. That's hysteresis. I think I got some sleep in my eye still. Which answer does not strengthen the electromagnetic field of an electromagnet? We were talking just strictly electromagnet. AC versus DC is what the issue is, or what the doesn't matter. That's what I'm trying to say. Sorry. Uh, Adding a core to an electromagnet is the easiest way to increase the strength of that electromagnet. And then we've already had a question earlier in the lesson that said adding current strengthens the electromagnet. The more turns of your coil that you have will also strengthen the electromagnet. Nobody put that, but you know, putting more turns makes a stronger magnet. It's just not something you can generally change once the electromagnet is made. All right. Oh. All right. I'm gonna go ahead and end this here. It looks like everybody. Yeah. Hey, look, everybody got good. let's start the new quiz. Transformers. Transformer operation principles. Alright, I will see you guys at 10:45. If you didn't get my message earlier, or a couple days ago, test pickup is happening between 11:30 and 2 now. You will have 3 tests to pick up. Take them home, work on them over these next 2 weeks. You can use your book and everything. And yeah, you should have everything you need to do these tests. Just go pick them up. Call the office if you're going to be late picking them up. And that's about it. All right, go pick up your test at 11:30, or between 11:30 and 2. All right. No, don't finish. End the stream. I'll see you guys at 10:45.